Welcome, welcome to the signal processing aspect of millimeter wave. So, we will be continuing the time series part today. So, today we will be covering the time series part, starting the lecture number 15, where we will be introducing the time series part, and that will be very much important when you go for the time sequence analysis, especially when you go for the Doppler. So, these are the concepts that which we will be covering here: introduction to the time series, then related parameters like autocorrelation function, and then power spectral density or PSD. So, these are the terms which we will be using very often in our discussion. Time series part. Okay. Now, let us define in very general way. Then we will map it to the channel part. Okay. So, in this case, what we are interested is basically a stationary time series. So, we are assuming that, let us assume that there is a sequence, let us say the sequence is y n, which was basically h l n in our case. Okay. Just drawing an analogy. So, I am defining a sequence called y n. So, y n is some sequence, maybe a time series, maybe a channel Lth tap can be one of such sequences. Okay. Now, this sequence it is a correlated sequence, and that is precisely why I am interested to know the time series here. We are assuming in this case that this sequence is a stationary sequence. It is a stationary sequence. Okay. Now, we are not modeling the non-stationary sequence here. What is non-stationary sequence? A sequence whose statistics completely changes after some time, which is not constant. Okay. If it is a stationary sequence, the statistics will never change. Okay. The PDF, the joint PDF of any number of sequences will never change. That is precisely the definition of a stationary sequences. If it is a non-stationary, y n minus 1, if I take the joint PDF, they keep changing. I mean, you can't say that y n minus 1 and y n minus 2 and y n minus 3, they will remain constant. We can't guarantee. That means, time to time the statistics would change. In this case, we are assuming it is a stationary sequence. Now, practically, is my channel a stationary channel? Practically not. Practically, it is completely a non-stationary sequence. But the advantage that we are taking there, the channel, whatever we are considering it, we are considering for a large time, and what is that large time is difficult to answer. It can be 1 minute, it can be 2 minutes, or it can be even be a 1 second also. So, it depends on the Doppler, context of Doppler. Okay. So, there is a Doppler, and there is something else we will be discussing it. There is a something called coherence time. We will discuss that later. But let us assume that I am considering a time over which my channel's statistics do not change. Channel may change. Okay. Channel may change because something moves here and there, because of the Doppler channel may change, but statistics do not change. Okay. When it can be can we assume some scenario where we can think of the statistics do not change and statistics changes completely. Say for example, we are walking in a busy street of a road, okay, busy street of say Kolkata. We are walking for 10 minutes, 15 minutes. For 10-15 minutes, the nature of the environment would remain almost same, right? The number of cars, number of people, houses and all more or less, I mean exactly they may change, but more or less it is like a statistically they may remain same. So, I can say if the time, of course, when I am walking through such kind of environment, my channel content will be changing, but would the statistics of my channel change? Need not be, because more or less it is the same. But now you assume a scenario, you are walking through that street of a busy street of a particular city, and then after walking for say 1 hour, you suddenly enter into a village, okay, or suddenly enter into a very enter into a region where there is no houses, okay, not many cars are also there. Now, think of that scenario. So, here of course, channel values are changing, but channel statistics may also change in that case, because the environment completely changes statistically in a very, very drastic way. So, such kind of scenario I can think of that the in such kind of scenario, you can think of a channel statistics changes from time to time. So, now you can imagine how often such things happen. Does it happen so often? Does it happen just after 1 microsecond my channel statistics changes completely? That means, after 1 microsecond you have to enter into a region where objects, the nature of the objects, the number of objects will be completely drastically changed. That does not happen. We do not we do not move in such a high speed. We are not moving close to the speed of light. We are moving in a normal. Even if you are in a train, probably high speed train could be some 200 250 kilometer per hour or something like that, or in a general train 100 kilometer per hour or 80 kilometer per hour, or a car. So, in there, at least for some significant amount of time, I can say my channel statistic will not change so much, okay, because the regions, the geographic regions are not so small where things will change so fast. So, which means that though our actual system or actual channel is a non-stationary system, but for a considerable amount of time I can assume my channel statistic remains same. That means, it is a piecewise stationary. So, such kind of real system is called a quasi-stationary. So, our consideration of channel is basically that. So, you have a long time. So, how long it is, it is difficult to even quantify that. Tentatively is some time. So, let us say a large time, I do not know, maybe 10 minutes, 15 minutes, it depends on again your Doppler, right. If you are traveling in a train, probably after 5 minutes you may encounter a different geographic locations, okay, or maybe half an hour good enough. If it is a plane, probably not in the sky, but at least when it is in the ground, it encounters changes very fast. So, it all depends on the Doppler. So, let us assume that I have a time where my channel do not change the statistics. So, I can say during this t time, or rather a t1 time, it is a stationary process. Again, for t2, the channel statistics do not change. Channel values may change, but not the statistics. That what is meant by statistics? The PDF. We have shown earlier, right? The channel is more or less a complex Gaussian nature with some mean and variance, right? Mean was supposed to be 0 and some variance. I am talking of that quantity. Say mean becomes 0, let it remain 0, but variance do not change if it is a Gaussian. So, I am saying that throughout T1, the variance of the channel would remain constant. Throughout T2, the variance of the channel would be something else, but it remains constant. So, that way. So, this kind of thing I call it a piecewise stationary or rather quasi stationary. So, this is a quasi stationary. Now, in this time series, whatever we are going to explain it, we are considering a stationary system, meaning we are assuming that we have enough time for which my statistics do not change. So, under a stationary sequence, what should be my channel modeling in terms of time series. So, now let us say y n is such a random sequence that could be Lth tap itself at a time n. Okay. So, there are 3 ways we can model the time series. One way is called autoregressive. Or it is called AR. Okay. Another one is called moving average. Okay. So, this is called MA, and the third one is a mix of both. So, it is autoregressive moving average, rather we call it ARMA. Okay. So, there is an order whenever we talk about the time series, there is an order associated with, just like your polynomial, every polynomial has an order, right. So, AR, when you say AR, it should have an order. Order of what? Of what order? So, I will say order P order. So, say AR time series, AR model of time series with order P. It is a MA order of time series with order Q. It is an ARMA order of time series, order P and Q, both will be there. Okay. So, we will explain it in a very simple mathematical logic what exactly autoregressive, what is moving average, what is ARMA process. Okay. So, these are the three ways you can define a time series. So, basically it is the three ways you can define the correlation. Correlation between what or among what? Among the sequences that you already have it at, say, at mth sequence with respect to its previous sequences. So, that is exactly what we wanted to have it here, right. This is precisely what we wanted to have it here. No? So, this is the channel at, so this is the channel at say m plus 1 or rather 2 m equal to 2. I want to know what is its correlation with m equal to 1 and m equal to 0 and so on and so forth, okay, like that. So, here also we want to have that definition. So, let us say what is the AR model, autoregressive model. So, if I have a sequence yn, okay. So, if it is AR 1, order 1, what is the definition? It is defined something like that, A y n minus 1 plus E of n. Okay. So, A is basically some sort of a known coefficient, E n is completely an independent random process. So, this is a random process, not random process, I would say it is independent you can say even an identical process also, I do not mind, identically distributed process. And this introduces that randomness we are talking, that between m equal to 1 to m equal to 2, the channel, how they are correlated? They are correlated, but there is a delta h we are talking, right. So, that is the extra part which we want to model it as some sort of a randomness. So, this is basically that delta h part. Okay. We are assuming that that particular delta h is some sort of a completely an independent process going on. So, this E n is basically an independent process, identically you can assume independent identically distributed process, IID process. Okay. And now you look at the correlation. So, this defines or this creates that correlation factor. So, y n is correlated with y n minus 1 through this quantity A. So, this kind of, so basically it is a regressive model, right. If you have learnt what is called IIR filter, it is what in basically it is kind of a y n is dependent on y n minus 1 and so on and so forth, right. So, these are all a regressive process. So, here also the same thing kind of happening here. So, y n depends on the previous y n minus 1 through a constant called A, and A is known to you, that is not a random variable. Now, the only random part that is getting introduced here is the E n part. So, through E n, y n becomes a random quantity, but y n and y n minus 1 is correlated. Okay. So, this is called a AR1 modeling. Similarly, I can I can generalize it, say I want to have it 2, say in fact I want to have say 2, I mean AR order 2. So, how can I do A1 say y n minus 1, or I put it this way. Plus A1 y n minus 1 plus E n. So, this is your AR2 model. I can even generalize it. Now, I will introduce the ARP. So, now what is AR2 model? AR2 model meaning the y n depends on two previous data. One previous data is this, another previous data is this, y n minus 1 and y n minus 2. It depends on that. Okay. And these two are constant. This is a known constant. So, that creates the correlation, and this one creates the randomness inside the y n. So, this is called AR2 process. Now, what is the natural extension of this process? So, let us say it is ARP model. Let us say I have ARP model, pth order ARP. So, what can I say? This is A of p, right, and this will be y of n minus p happening plus dot dot dot, finally you will get A1 y n minus 1 plus E n. So, this is your ARP model. So, ARP model. So, that means the y n depends on p number of previous values, p previous time values will be there, y n currently depends on all of them. Okay. So, this is kind of a ARP model. Okay. Next one. Okay. So, this is clear. So, ARP model. Now, before I get into the moving average model, I want to introduce some more operator. Okay. So, there is an operator called B operator. It is easy for us to introduce this B operator, because it will make our spectrum calculation very easy. Okay. So, this is a B operator. Ultimately, that is what we want, right? We want to get the spectrum, how much extra spectrum that appears for me due to the Doppler. That is precisely my goal is, right. So, this is one case B operator. Okay. So, let us introduce that B operator. So, B operator is called a backward operator. So, this is also called backward operator. Okay. It is called a backward operator. So, the definition of this one is that if y n is a sequence and I give an operator, operator is some sort of an, you can say it is an operation to be done on a particular mathematical notation. So, that is an operator. So, it means that if it is a b y n, it is nothing but b y n minus 1. It is just an, you can say it is a notational way of say expressing it. And if it is b to the power j y n, it means it is y n minus j. Just a definition. This is an operator. Okay. Now, with this operator, I can express my ARP process very simply. In a very simple way, I can express my ARP process. Similarly, I can express my MAQ process or ARMA P of Q process can also be expressed in a very, very simplistic manner by this operator. Now, there is a very good advantage of this operator. The advantage of this operator is that you really do not have to go through the pain of autocorrelation function generation for spectrum evaluation. This makes this life of this makes our life of generating the spectrum very easy if we use an operator. Okay. That is why I directly get into the operator rather going into the autocorrelation, but I will define autocorrelation, because autocorrelation will show some other properties. Okay. But let us first close our main intention of spectrum part. So, this is an operator. Okay. Now, let us see how I can express my ARP process using the operator. Okay. So, what can I say? If I look at this y n and ARP process, I can always write it. So, finally, can I write it like that? If it is an ARP process, this is A of p, right, b to the power p y n plus A of p minus 1 b to the power p minus 1 y n, and so on and so forth, right. What it would be A 1 b y n plus E n. This is what I will get if I use an operator, right. I just do some mathematical jugglery here. Can I write it like that? I just put the y n this side, left side. Okay. This is precisely what I have done. Now, what is this? Some sort of polynomial, right, standard polynomial, I get it. So, can I write it like that? So, if I say y n by E n, right. So, what can I say? See what is written here 1 a minus b and so on so forth. I will write it like 1 minus a 1 by a 1 b minus a 2 b square dot 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 minus a of p b to the power p. This is what I can write it, correct? This is what I can write it, right. So, it is as if like again I am having some sort of a FIR filter, this AR model, right, where I am giving En as an input to the system. So, let us this whole thing I call it say some notation say Z of B. So, it is as if like I am giving En as a sequence or input sequence to a system, linear system B, and I am getting an output y of n, where this Z B itself is an FIR filter of order P. I can think of that way. So, this whole ARP process I convert it to a simple input output relationship, simple input output system, where I have some sort of a filter kind of things. So, now what is my job? So, it is as if like I am giving En, I am getting Yn. What is my job? My job is to know what is the spectrum of ZB. That is precisely what I want to know, right. So, that means what is the spectrum this particular fellow gives me. I can have two ways of evaluation. One is this B operator. This B operator is simply saying this is nothing but some sort of a FIR filter, right. So, now what is my job? I want to know the spectrum of FIR filter. How do I get it? Spectrum of FIR filter? Well, you replace B, because what is B? B is a backward operator. Now, how do you replace, how do you imagine a backward operator in your signal processing? It is like a Z operator, right, the Z inverse. You have seen in the context of DSP, this is Z inverse is nothing but a backward operator, right. It is basically a delay operator, right. So, B is also like something like that, it is basically a delay operator. So, which means you just replace B is equal to e to the power minus j omega into this filter. What will I get? I will get Z of Z of omega, whatever it will be. It will be 1 minus a 1 e to the power minus j omega dot dot a p e to the power minus j omega p. This is what it will be coming, right. I want to know the spectrum of it. So, what should I do if I want to know the spectrum? Naturally, I want to know how this is plotted. So, that gives me the actual spectrum or power spectral density. Basically, this is the power spectral density, right. So, this will give me the power spectral density. This is my power spectral density, because that is what I want to know. How do I get a spectrum? Only from power spectral density. So, you plot the power spectral density, see where the power is existing, that is your spectrum. Okay. So, I want to calculate that. So, can I write it like this? So, you can calculate it. So, here you know what it is. So, take Z omega and they take the conjugate of it, you are done. Okay. So, that is a very simple way of calculating the power spectral density, or the power rather, not power spectral density, which will eventually give you the amount of spectrum that this particular Doppler holds it, right. Okay. So, that is a very easy way of getting it. So, there is a second way of getting it. Okay. So, this is one way of calculating my spectrum. So, from here you can know what is your spectrum, you can evaluate your spectrum, but here the catch here is you have to know all these coefficients. All these coefficients have to be known, otherwise it is not possible. These coefficients have to be known. Okay. Okay. So, I do not have to do any Fourier transformation or anything like that. Just take the B operator, create an input output relationship, replace B equal to the power minus j omega and take the mod of it, that whole one is mod square, that gives you the power spectral density. Is there any other way to come to the power spectral density? Yes. So, if the sequence is say yn, it is a random sequence, what I can do? I can create an autocorrelation function. Let us call it R of k. Now, we have assumed it is a stationary process. So, it really does not depend on n, that is the advantage we are getting. So, what is R k? How do you define R k? So, R of k, you define its expectation of your y of n and y star of n plus k. Okay, so we can define it. Now, if it is an if it is a stationary process, then R k and R minus k both will be equal. In that case, you find out what it is. Then what? How do I get a power spectral density of it? So, the same thing, this mod z square, right? The same mod of z omega square. You get it by take a Fourier transformation of your R k. Take a Fourier transformation of R k and you get z omega square. But there is a slight difficulty here, because first you have to get the autocorrelation function. Once you get the autocorrelation function, you get the a sequence. Okay, you get a even sequence k minus and plus both sides, you get a sequence. Then you have to take a Fourier transformation on that. Okay, and then you just get a, in this case you cannot get a Fourier transformation, it is a DTFT, just take a DTFT on that, you will get z omega square, because it is a discrete sequence, you get z omega square. So, this is another way of getting your spectrum or power spectral density. Yeah. So, from there you can get a spectrum. So, it is another way of getting your power spectral density. Now, we will try to do some example on the autocorrelation aspect here and see what exactly our power spectral density comes into picture here. Okay. Okay. So, this was the model that we get it after the B operator. So, this is the input out. Now, you think that is kind of an input output relationship, right, using the B operator. So, this is y n is equal to some polynomial whatever I have written here, and then E n. So, what I can think of? I can think of it something like that. I can think that if y n comes here, y n by E n I put it is equal to this whole thing, whole inverse, I will put it like that, right, because this is what it is. It's y n is in the left side, E n is the right side, and there is this whole polynomial part is present here, pth order polynomial present. Now, y n by E n you take the other side, the whatever is there inside the red part, you take it in the other side, right side. So, what will I get is y n by E n is equal to this whole thing inverse, this whole thing inverse will be there. Okay. Now, what can I think of? This whole thing I can think of it as an input output relationship with some linear model, right. Now, in this case, let us call this as a ZB, this whole thing I call it as a ZB, some polynomial factor, right. I mean, you can think of it as some sort of a transfer function. What does this transfer function represent? You think that this transfer function is representing it's like an IIR filter, infinite impulse response, right, because this is whole to the power inverse. So, now I can say this whole thing can be modeled as if like I have an input E n which gives me an output y n. It goes through a IIR filter called ZB, which has a transfer function 1 minus a 1 b to a p b to the power p whole to the power inverse. So, that is kind of an IIR filter you can think of, and E n is going through that IIR filter and I am getting that y n. I can think of that way, right. Then how do I get a spectrum? I get a spectrum. How do I get a spectrum of it, or how do I get a power spectral density of such kind of transfer function? Just replace the z operator in a normal case, right. In a normal filter, you replace the z operator by e to the power minus e to the power j omega. Similar thing you do it here. Here B is equivalent to that Z inverse, because it was a delay element, right. So, just replace B by e to the power minus j omega. What will you get? You will get some z omega, you will get that particular, things you will get it 1 minus a whole inverse, that because it is just an IR modeling. And then what you get? You get a z omega square and everything you will get it as it is. You get actually a power spectral density, right? Because if you know what is z omega, what will you get? You get everything, you get the power spectral density. How do you get a power spectral density? You replace the b by e to the power j omega, you get the omega domain data and just take the conjugate and multiply it, you get the power spectral, you get the power spectral density. So, what is power spectral density? It is nothing but mod of z omega square. That is exactly your power spectral density. You plot it, you get a power spectral density. Same thing we have done it here. You get a power spectral density using z omega square, you get spectrum and so on, so forth. Now, same thing you can use autocorrelation. Okay. So, what is the definition of autocorrelation of a sequence? Autocorrelation of a sequence, if it is a stationary sequence, it will be defined as expectation of y n into expectation of y n into y star n plus k. So, that is the definition. We will do some mathematics, we will do some examples how to get an autocorrelation of a simple sequence, we will do that, but that is the definition of an autocorrelation. So, once you get an autocorrelation, again I am kind of half done for power spectral density estimation, because to get the power spectral density you have to take a Fourier transformation of it. Now, here you cannot do a Fourier transformation, you can take a DTFT of that, because it is a discrete sequence, right, because it is a discrete sequence. So, autocorrelation will also be a discrete sequence, because k is kind of, you know, it is a sequence. So, plus 0, plus minus 1, plus minus 2 and so on, it is an integer, it is a sequence, right. So, how do you get a spectrum of a sequence? Take a DTFT, as simple as that, and it will give the same z omega square. Now, there are problems here. What is the problem? First, you have to get autocorrelation, okay, which may not be so easy to get it, but for a given sequence probably it may be easier, but you have to do a lot of expectation operation and so on and so forth, and then you have to take a DTFT operation. Okay. Now, this is one approach of getting power spectral density, and other one which is a very simplistic approach is the one which I have just shown. Use B operator. It is like a filter, either you get a FIR filter or get an IR filter or get a mix and match. It is like a you have P and Q both, everything is like IR or FIR filter, you get it, and the job is to get the spectrum of the IR filter. So, you replace B by e to the power minus j omega, done, you get a power spectral density. Okay. Okay. So, that is the reference book, Time Series Analysis, Forecasting and Control by George E. P. Box. Thank you.